In this video, we're going to look at the solutions to all of the problems on the 2025 AMC 12B. Okay, let's jump right into it. So the first one says, the instructions on a 350 gram bag of coffee beans says that proper brewing of a large mug of pour over coffee requires 20 grams of coffee beans. What's the greatest number of properly brewed large mugs of coffee that can be made from the coffee beans in that bag? So there's not really anything going on here. All you have to do is take 350 and divide it by 20, and you'll see that we get a quotient of 17 and a remainder of 10. So that means that, well, the number is 17. You can get 17 large mugs of coffee. Okay, now on to the second problem, which says Jerry wrote down the ones digit of each of the first 2025 positive squares. So for example, 1, 4, 9, 6, because that's the ones digit of 16, 5, because that's the ones digit of 25, so on and so forth. What's the sum of all of the numbers Jerry wrote down? Okay, so the idea here is to look at the perfect squares mod 10. In other words, look at their ones digit. But since you can square before or after reducing mod 10, you only need to look at the numbers between 0 and 9. So let's do that. So let's say we're looking at all of the numbers x mod 10 and then all of their squares. So I'll just write that as x squared mod 10. And let's make a little chart here. So we need to look 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let's square each of those. So 0 squared is obviously 0, 1 squared is 1. Here we have 4, 9, 6, because that's 16. 25, that gives us 5. 6 again, because it's 36. 9, 4, because we have 8 times 8 is 64. And then 1, because we have 9 times 9 is 81. But now let's observe that if we take this sum right here, we'll get what? Well, it's pretty easy to calculate. We'll get 45 of these. But now what we'll observe is that we'll have this sum that's equal to 45 202 times. And we can see that pretty easily because this is for the numbers 0, 1, 2, all the way up to 2019. So 0 squared, 1 squared, 2 squared, all the way up to 2019 squared. It's just we're looking at 45 because we're reducing all of these numbers mod 10, and then we're squaring and then reducing that mod 10. So that's why we have that list up there. And then after that, we're going to have the numbers associated to 2020 squared, 2021 squared, all the way up to 2025 squared. So let's see. That's going to give us 0 plus 1 plus 4 plus 9 plus 6 plus 5. So here I'll just point out that this is for the numbers 2020 up to 2025. But now that's a fairly straightforward arithmetic problem, and what you'll see is that in the end you get 9115. Okay, let's move on to the next problem, which is to find this product I times I minus 1 times I minus 2 times I minus 3, where I is the square root of minus 1. So in other words, I squared is -1. And so I'll just do this like one piece at a time. So let's observe that if we do I times I minus 1, we'll get I squared, which is -1, and then we'll have minus I from distributing that through. So I guess we could color code this if we wanted to be like really thorough. So those two match with each other. Then we'll multiply out this I minus 2 times I minus 3. So we'll have I times I, which is -1, and then that'll be plus -2 times -3, so that's going to be plus 6. So that means our real part will be 5. And then for our imaginary part, we'll have minus 2i minus 3i, so that's going to be minus 5i. Now what I'll do is I'll factor a -5 out of that, and that's going to leave me with I plus 1 times I minus 1. Or sorry, 1 plus I times 1 minus I. Now, if we multiply 1 plus I times 1 minus I, you'll see that you get 2. So in the end, we have minus 5 times 2, or minus 10. Okay, moving on. The value of a 2-digit number AB in base 7 is equal to the value of a 2-digit number BA in base 9. And then our goal is to find A plus B. Okay, So they use this underline notation for digits of a number, but I like this overline notation a little bit better. I kind of think it's more standard. So we have number with digits A, B, and base 7 is equal to the number with digits B, A, and base 9. But now let's observe that means that 7A plus B is equal to 9B plus A, just by the definition of base 7 and base 9. And let's observe that we know A and B must come from the set 1, 2, 3, all the way up to 6. We know it can't be bigger than 6 because we're in base 7 over here, so it has to make sense as a base 7 number. We know neither of those can be 0 because we're told that they're both 2-digit numbers. So A can't be 0 because this left-hand side is a 2-digit number. B can't be 0 because that right-hand side is a 2-digit number. Okay, but now let's observe that tells us that we have 8B minus 6A equal to 0, just moving some stuff around. Now we can factor a 2 out of that, and we'll see that we have 4B minus 3A is equal to 0. But then from there, just keeping in mind that A and B only come from that set 1 to 6, we only get a single solution, and that's going to be A equals 4, B equals 3. So that tells us A plus B, which is our goal, is equal to 7. Okay, next problem. And it says positive integers x and y satisfy the equation 57x plus 22y equals 400. What's the least possible value of x plus y? Okay, so let's maybe just get that defined equation on the board. So 67x plus 22y equals 400. Now what I'm going to do is move some things around here. So let's write this as 22 times x plus y. The motivation for that is because our goal is to determine that smallest possible value of x plus y. So I'd like to get x plus y into this situation. But after rearranging things, this is going to be equal to 400 minus 35x. That's what's left over. Now what we can do is factor out a greatest common factor from this right-hand side. That'll give us 5, and then 80 minus 7 times x. But now let's observe that 22 and 5 are relatively prime. That means that this 80 minus 7x must be a multiple of 22 because 5 doesn't share any factors with 22. So in other words, we have 80 minus 7x is equal to 22 times k. But that tells us that 7x is going to be equal to 80 minus 22 times k. But now notice there's only going to be so many possibilities of this that are positive integers. We're just looking for the one that is a multiple of 7. So let's maybe just write that out for some values of k. So this is going to be 80 if k is equal to 0. This is going to be equal to 58 if k is equal to 1. It's going to be equal to 36 if k is equal to 2. It's going to be equal to 14 if k is equal to 3. But let's observe that this 14 is really our only possibility because we need a multiple of 7 over here, and none of those are multiples of 7. So that tells us that 7x is equal to 14. In other words, x is equal to 2. But now what we can do is take this value of x being equal to 2 and plug it up here into this equation. So let's see, that's going to give us 22 times y plus 2 is equal to 5 times, now we're going to have 80 minus 14. But 80 minus 14 is 66. So now what we can do is take this 22 and cancel this 66 down to a 3, and we'll have y plus 2 is equal to 15. In other words, y is equal to 13, but that means that x plus y was equal to 15. Now I guess we could have had a quicker out here just by noticing that this value of k equals 3 is associated with this thing being equal to 66, and then we can use this equation right here to solve for x plus y without ever explicitly writing down the value of x. And that's a shortcut you might want to take on the test day, but just to see a full solution, I think it's fine right now to get values of x and y. Okay, moving on. Emmy said to Max, I ordered 36 Math Club sweatshirts today. Max asks, how much did each shirt cost? Emmy responds, I'll give you a hint. The total cost was ABB.BA dollars. So in other words, it's like $100, and then B would be the tens of dollars, B would be the ones of dollars, and then we've got BA cents, where A and B are the digits, and A is not equal to 0. After a pause, Max says, that was a good price. And then our goal is to find A plus B. Okay, so what I'm gonna do is write this whole thing in cents instead of in dollars and cents, just so that we're within the integers. So let's observe in cents, we have the following equation. We have A, B, 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 A, so that's our 5-digit number, is equal to 36 times x, where x is equal to the cost per shirt. Because let's recall that we were selling 36 shirts. But now let's notice that the right-hand side of this is divisible by 9. That's because, remember, our cost is in cents, so that means we've got whole numbers on both sides. So anyway, the right-hand side is divisible by 9, but that means that the left-hand side is divisible by 9. But the left-hand side being divisible by 9 means that the sum of the digits on the left-hand side is divisible by 9. That's a standard divisibility by 9 trick. So let's just write that down. So divisible by 9 will imply that 2 times A plus 3 times B is congruent to 0 modulo 9. Okay, nice. But now let's observe that that means that 2 times A is congruent to 6 times B mod 9. So that's just subtracting the 3 over, keeping in mind that -3 is 6 mod 9. But now we know that 2 is invertible mod 9, so we can divide both sides by 2, and we'll get that A is congruent to 3 times B modulo 9. Okay, so this is a bit overkill, but let's make a chart where B is like our independent variable and A is our dependent variable. And what we're doing is looking at all of the possible values of A given the possible values of B. So let's see, B can be equal to 1, 2, 3, 4, 5, 6, 7, or 8, or I guess 9. Because notice that B has to be a digit between 1 and 9, given that the rules that we have right here. Great. And then, well, let's look at A. What we can do to look at A is, well, multiply B by 3 and then reduce it mod 9. But then instead of keeping 0 mod 9, we'll keep 9 mod 9 as the 0, just because, again, we're looking at digits between 1 and 9. Okay, so let's see. This is going to be 3, 6, 9. And then let's see, 3 times B is 12 in this case, but 12 is 3 mod 9. 3 times B for 5 is going to be 15, but 15 is 6 mod 9 because it's 6 more than 9. And then you can see that this whole thing is going to repeat. So we're going to get a 9 here, and then a 3, a 6, and a 9. And now let's notice that the last digit of our price here is A. But our price is also even, so that means that A has to be an even number. So that means that we really only have these possibilities right here. B is equal to 2, A is equal to 6. We have B is equal to 5, A is equal to 6. And B is equal to 8, A is equal to 6. Now let's also observe that this thing is divisible by 4. But since this thing is divisible by 4, that means that the last 2 digits, BA, is divisible by 4. That's a divisibility by 4 rule. So a number is divisible by 4 if and only if its last 2 digits are divisible by 4. But let's observe that from this chart right here, we have the possible last 2 digits, 2, 6, 5, 6, and 8, 6. But let's observe that the only pairs of those that are divisible by 4 would be the last 2 digits, 5, 6. But that means that, well, we've got our answer. And in fact, we can use that to find a plus b. So a plus b is equal to 11. Okay, so let's move on. So our next problem is to determine this sum as n goes from 2 up to 255 of the log base 2 of 1 plus n over the log base 2 of n times the log base 2 of n plus 1. So the trick here is to observe that this log base 2 of 1 base n, or 1 plus 1 over n, is the same thing as the log base 2 of n plus 1 over n. I think, well, that's pretty clear after you see it. So that's going to give us this sum as n goes from 2 up to 255 of the log base 2 of n plus 1 minus the log base 2 of n all over the log base 2 of n times the log base 2 of n plus 1. Okay. Now what we'll do is split that fraction up into 2 pieces and have the denominators cancel a little bit for each piece. So now we've got this sum as n goes from 2 to 255 of the log base 2 of n plus 1 will cancel in this first one, giving us 1 over the log base 2 of n minus 1 over the log base 2 of n plus 1. Okay, cool. But now what you'll see is that this telescopes pretty handily. So let's observe that the first term will be 1 over the log base 2 of 2 minus 1 over the log base 2 of 3. The second term will be 1 over the log base 2 of 3 minus 1 over the log base 2 of 4 plus ... That last term will be 1 over the log base 2 of 255 minus 1 over the log base 2 of 256. But let's notice these things canceling. So this log base 2 of 3 will cancel this one. The log base 2 of 4 will cancel something that comes after. The log base 2 of 255 will cancel something that comes before. And we're left with 1 over the log base 2 of 2, which is clearly 1 over 1, minus 1 over the log base 2 of 256. But 256 is 2 to the 8, so that makes this 1 over 8. So in other words, our final answer here is 7 over 8. So for the next one, it says there are integers a and b such that the polynomial x cubed minus 5x squared plus ax plus b has 4 plus the square root of 5 as a root. What is a plus b? Okay, so here's the idea behind this. So, well, let's just get this polynomial on the board right here. So we've got x cubed minus 5x squared plus ax plus b has 4 plus the square root of 5 as a root. But it's important to point out that if it has 4 plus the square root of 5 as a root, since we have all integer coefficients, it also has 4 minus the square root of 5 as a root. But that means that we can rewrite this as x cubed minus 5x squared plus ax plus b equals x minus 4 plus the square root of 5 times x minus 4 minus the square root of 5 times x minus, and I'll just call this capital A for the third root. We know that it's going to have 3 roots because it's got 2 real roots, which means it's got to have 3 real roots because complex roots will come in complex conjugate pairs. Okay, so now the idea is to multiply out this right-hand side. So let's do that just a little bit at a time. So those first 2 terms will multiply together to give us x squared minus 8x plus 11. So you just have to be careful with the arithmetic there. And then we have that multiplied into x minus a. And then further multiplying this whole thing out, you'll see that you get x cubed. And then what will the x squared term be? Well, notice that it's going to be minus a plus 8 times x squared. So the x squared term is this negative a minus 8, but we'll just factor the minus sign out. And then let's see, what's the x term? Well, it's pretty clear that the x term is 8 times capital A plus 11, and then the constant term is minus 11 times A. Okay, well, I think that's pretty good. Now that gives us this nice system of equations that we can get from extracting coefficients. So let's observe that extracting the coefficient of x squared will tell us that capital A plus 8 is equal to 5. The coefficient of x will tell us that 8 times capital A plus 11 is equal to lowercase a. And then the coefficient of 1, in other words, the constant term, will tell us that minus 11 times a is equal to b. And now from here, we can pretty easily solve this system of equations. So observe that this right here tells us that capital A is equal to negative 3. But then looping that into the equation that's just below, we'll see that lowercase a is equal to minus 13. And then finally, looping that into the bottom equation will show us that b is equal to 33. But let's recall that our goal is to find this a plus b. But pretty clearly, if we do a plus b here, we'll get 20. Okay, so our next problem is to find the tens digit of 6 to the 6 to the 6. Now, notice that 6, our base here, is not relatively prime to 100. Now, finding the tens digit kind of points us towards reducing this thing mod 100. But since, like I said, it's not relatively prime to 100, we can't really use Euler's theorem directly. But we can kind of hack together something. So let's observe the following, and that is that 6 to the 6th power is most definitely an even number. But that tells us that 6 to the 6 to the 6 is equal to 6 to an even power. But since it's 6 to an even power, it's going to be a multiple of 4. Because notice that 6 is a multiple of 2. You multiply 2 multiples of 2 and you get a multiple of 4. So that means this thing is congruent to 0 mod 4. And that's where I'm talking about we're hacking together this reduction mod 100 by doing it mod 4 and mod 25. Notice that working mod 25 is a little bit easier because we can use Euler's theorem. So notice that Euler's theorem will say that if we work with the base mod 25, then that means that this first exponent will work mod phi of 25. But it's pretty easy to calculate phi of 25, that is 20. So that means this first exponent goes mod 20. But now notice that we can't apply Euler's theorem again and say that this second exponent goes mod phi of 20 because 6 and 20 are not relatively prime. Now you could hack it together again, or you could just make a little bit of a chart, and I think that's probably our best bet here. So let's look at this. Let's take maybe n here, and then we'll look at 6 to the n mod 20. Working up to n equals 6. So here we'll have 1, 2, 3, 4, 5, 6. And so let's see, we'll have 6 to the first power is 6. And then 6 to the second power mod 20 will be 16, because that's 36. That is going to be 16 more than 20. But notice that 16 is the same thing as negative 4 mod 20. I think it's probably a little bit easier to work with negative 4. But now if we multiply that by 6, we'll get 6 cubed. That gives us negative 24. But notice that negative 24 is the same thing as negative 4 again. But negative 4 again is just 16. So what we see here is that we just get a repetition of 16, 16, 16, 16. And we can see that pretty easily because after the first stage, if we multiply 16 by 6, we'll get 16 again mod 20. Okay, so that leaves us with 6 to the 6 to the 6 is congruent to 6 to the 16 mod 25. But now let's observe the following, and I'll just like maybe put this as a note, and you would maybe need to do this calculation on your own to convince yourselves of this. But 6 to the 5 is congruent to 1 mod 25. Okay, but that means that 6 to the 16 will be just congruent to 6 mod 25. That's because it's 6 to the 15 times 6 to the 1. But 6 to the 15 is 1 by this over here. But now let's see what we've got here. We've got 6 to the 6 to the 6 is 0 mod 4, and 6 to the 6 to the 6 is 6 mod 25. So if you start just like listing all of the numbers that are 6 mod 25 until you get a multiple of 4, you'll see that 6 to the 6 to the 6 will be congruent to 56 mod 100. That's the only one that will satisfy those two conditions. But that means that our tens digit is the number 5. Okay, let's move on. And the next one is a bit of a geometry problem. So the altitude to the hypotenuse of a 30, 60, 90 right triangle is divided into two segments with lengths x and y by the median to the shortest side of the triangle. What is the ratio of x over x plus y? Okay, so let's get a picture of that on the board. Okay, so there's our sketch of our 30, 60, 90 right triangle. The important thing here is I've got a right triangle. I wasn't super careful about making sure those other angles were correct. But now I'm gonna put this in the coordinate plane. So I'll extend this bottom side out into the x-axis. So I'll just do that with this dotted line. And then I'll extend this vertical side into the y-axis. And so that means I've put this point where I've got my right angle at the origin. So I'll just put here, this is 0, 0. And then I'll scale this thing so that this point over here is 1, 0. But then if I do that by the Pythagorean theorem and the fact that we've got a 30, 60, 90 right triangle, we know that this point up here will be 0 square root of 3. Okay, nice. Now what I want to do is get the altitude to the hypotenuse into this picture. Okay, so there's our altitude to our hypotenuse. So I'll just point out here that this is going to be a right angle. And furthermore, I'd like to figure out what this point is and find the equation of this line, which is built from this altitude to our hypotenuse. So let's extend that out into a line just to point out that that's what we're going to go for. So here we can get this started by observing that our hypotenuse is a line with equation y equals negative square root of 3 times x plus square root of 3. So the slope is pretty clearly negative the square root of 3 and the y-intercept is square root of 3. But then since this is an altitude to the hypotenuse, we know that it has to have a slope which is a negative reciprocal. So that tells us the equation of this line is y equals 1 over the square root of 3 times x. The y-intercept here is the origin, so we don't need that. Okay, so we've got our altitude to our hypotenuse in there, but there was one other part to this problem, and that is the median of the shortest side. So let's get that in there as well. Okay, so there's the median of our shortest side, but the fact that it's the median, we know this coordinate right here will be the coordinate 1/2, 0. But then, since we know that coordinate, it's a pretty easy exercise to go ahead and find the equation of that line as well. So here, I'll sneak that in like this. So the equation of this line is going to be y equals negative 2 times the square root of 3 times x plus the square root of 3. So it has the same y-intercept as my previous line, but it's just the slope is, well, twice as much. Now let's recall in the problem that this median is going to split this altitude into two pieces. In the problem they were called x and y, but since we've put this in the plane and we're using x and y as our equations of lines, I'm going to instead call these lengths here a and b. But that means that our goal, instead of finding, what was it, x over x plus y, our goal is to find a over a plus b. Okay, so we'll do this by perhaps finding this point of intersection right here, and as well this point of intersection. And then from that, what we can do is just use the distance formula a couple times to measure those lengths and then directly make that calculation over there. Okay, so let's maybe start by finding this intersection point. So that'll be the intersection point of these two lines. So that means the x coordinate will satisfy the equation 1 over root 3x equals negative root 3x plus 3. Now, maybe I'll leave the details to you, but you can solve this pretty handily, and you'll see that you get an x value of 3/4, and you'll get a y value of the square root of 3 over 4. Okay, so let's put that coordinate right here. Maybe I'll put it in blue because I'm using this blue arrow. So like I said, that's 3/4, and then the square root of 3 over 4. Okay, nice. Now we can similarly find this intersection point right here, which I'll maybe use pink for, and that's going to be the intersection of our green line and our pink line. So I'll put a pink dot here just to say that we're finding that point. So here we'll have 1 over the square root of 3 times x equals minus 2 root 3x plus root 3. So now solving this for x, you'll see that after a fairly straightforward calculation, you get 3 over 7. And then plugging that into one of the equations that we have, we'll see that y is equal to the square root of 3 over 7. Okay, so that means that we can sneak this in right here. This is the coordinate 3 over 7, and then the square root of 3 over 7. Okay, nice. And now let's measure these appropriate distances. So let's start by doing a plus b. Maybe that's going to be the easiest measurement to do because we're going from the origin. So that's going to pretty clearly be 9 plus 3 all over 16 because we're squaring 9 over 4 and we're squaring the square root of 3 over 4. So that's going to give us the square root of 12 over 4. In other words, it's going to give us 2 times the square root of 3 over 4. In other words, it's going to give us the square root of 3 over 2. So that's going to be our a plus b. Now let's calculate the distance b, and then from the distance b, we can get the distance a pretty easily. So let's see, the distance b is going to be 9 plus 3 over 49. So pretty similarly to what we had right here, that's going to give us 2 times the square root of 3 over 7. And then from that, we can calculate a just by doing the difference of those two. And you'll see that a will be equal to 3 times the square root of 3 over 14. But now finally, our goal is a over a plus b. So let's observe that that is 3 root 3 over 14 all over the square root of 3 over 2. So now when all is said and done, you'll see that that is 3 over 7. All right, now moving on. So the next problem is a probability problem. 9 athletes, no 2 of whom are the same height, try out for the basketball team. One at a time, they draw a wristband at random without replacement. The bag contains 3 blue, 3 red, and 3 green bands. They are divided into a blue group, a red group, and a green group. The tallest member of each group is named the group captain. What is the probability that the group captains are all of the tallest 3 athletes? So what we'll do is rename the colors so that the tallest player is on the blue team, the second tallest player is on the red team, and then, well, everything else is on the green team. Okay, so let's see how this is gonna go. So I'll just say, here's my blue team, and then here's my red team, and then finally here is my green team. Okay, so let's say, like I said, the tallest player is here on the blue team. And now what we want to do is look at the probability that the next two tallest players are not here. So in other words, the second tallest player and the third tallest player cannot be on the blue. Because remember, our goal is for the tallest player to be here, the second tallest on red, and then the third tallest on green. Okay, so what's the probability that this occurs? So there are 6 people to choose for the next person on the team, because we can't choose the second or the third tallest. And there are 8 total people to choose from. And then there are 5 people to choose for the third person on the team, because again, we can't choose the second or third tallest. And there are 7 total to choose from. And so that would be our probability of choosing the next 2 players without choosing the second tallest and the third tallest. Now, I guess we could simplify this a little bit if we wanted to. Notice that this is going to be the same thing as 3 over 4. So this is going to be 15 over 28. Okay, so now let's move on to the red team. So notice that the second tallest player will be here in our scenario. And then what we want is, again, the probability the next 2 tallest players are not on this team. So this is a similar calculation to what we just had before. Now at this stage, there are 5 people left to choose. We used 3 people to build the blue team. That leaves us with 6 people left. Then we put the tallest person onto the red team, or the tallest person left on the red team. That leaves us with 5 people left. Now, of those 5 people left, we can choose 4 to put on this team because we don't want to choose the tallest person that is left over. So that means we've got 4 over 5 probability for choosing the correct second person on this team. And then similarly, we've got a 3 over 4 probability of choosing the correct third person on the team. We've got 4 people to choose from now and, well, 3 people that are not the tallest left. So now we could do this calculation and you'll see that we get 3 over 5. But now that the red team and the blue team are totally built in the right way, we'll see that the green team is just okay, if you will. It will contain the third tallest person, maybe automatically, and then the other 2 players don't matter, if you will. So notice that our total probability will be just the product of these 2. So we'll have 15 over 28 times 3 over 5. But now that pretty easily simplifies to 9 over 28. Now, before we move on to the next problem, I'd like to sketch out another solution of this problem. And this second solution is maybe more of a direct counting argument. So I'd like to look at it like this. So we've got the number of ways to put the tallest players on different teams times the number of ways to build the rest of the blue team times the number of ways to build the rest of the red team times the number of ways to build the rest of the green team. And then, well, that's going to be all of the ways, or the number of different ways of building teams where the tallest are on a different team. And then we want to divide that by the total number of ways to build teams. And so that'll be the number of ways to build the blue team times the number of ways to build the red team times the number of ways to build the green team. So now, how many ways are there to put the tallest members on different teams? Well, that's going to be 3 factorial. And then the number of ways to build the rest of the blue team will be 6 choose 2, because we've got 6 players left. We need to choose 2 for the blue team. And then how many to build the rest of the red team? Well, that's going to be 4 choose 2, because at this stage we've got 4 players left. Choose 2 of them to fill out the rest of the red team. And then what about for the rest of the green team? Well, that's going to be 2 choose 2. We've got 2 players left, and from that we choose 2 of them. And then how many ways are there to build the blue team? Well, that's going to be 9 choose 3 because, well, here we've got all of our players. We're picking 3 of them to be on blue. And then this will be 6 choose 3, and this will be 3 choose 3 for similar reasons. But now you can just write out what all those binomial coefficients are in terms of, quotients of numbers. So like 6 choose 2 is going to be 6 times 5 over 2 times 1, and so on and so forth. And you'll see that this will all cancel down to 9 over 28. Okay, now moving on. This one's another bit of a geometry problem. So the windshield wiper on the driver's side of a large bus is depicted below. Arm AB pivots back and forth around point A, sweeping out an arc of 60 degrees symmetric about a vertical line through A. The wiper blade CD is attached to B at its midpoint and stays vertical as the arm moves. The arm is 3 feet long and the wiper blade is 3.5 feet tall. What is the area that the windshield is cleaned by the wiper in square feet to the nearest hundredth? Okay, so let's get a picture of this situation on the board. Okay, so there's our starting picture, but now I want to put a couple more copies of this on the board so we can get an idea of what's going on. And so I'm going to put a copy where A and B is vertical and then where A and B is tilted over here to the left as well. So the important thing to notice is that this line segment AB sweeps out a circle or maybe a slice of a circle as the windshield wiper goes back and forth. But then since C and D stay vertical, this point C is sweeping out an arc of a circle, and this point D is also sweeping out the arc of a circle. Okay, so let's maybe fill in these arcs just so that we've got them. Okay, so good. Now the idea is to cut and paste until we get a rectangle. So let's take this portion right here and we can cut that and then paste it down here. But notice that if we cut that and paste it down here, we have a rectangle and we know that this is 3.5, just given that CD was length 3.5. Then we just have to figure out the width of the rectangle. But let's observe that the width of the rectangle is going to be the same as this chord length right here, where this angle is 60 degrees. But we can calculate that chord length using kind of a standard formula for the length of a chord given an angle, which is 2 times the radius times the sine of that angle over 2. So this is going to be 2 times 3 times the sine of 30 degrees, given the fact that we've got this angle is 60 degrees. But that calculation will give us the number 3. So that means this width down here is 3. So now we've got the height and the width, which means our area is simply equal to 3 times 3.5. In other words, it's 10.5. And that's not like an approximation, that's the exact area. So the next problem is a counting problem. So a circle has been divided into 6 sectors of 6 different sizes. Then 2 of the sectors are painted red, 2 green, and 2 blue, so that no 2 neighboring sectors are painted the same color. One such coloring is shown below. How many different colorings are possible? Okay, so let's get a couple of these pictures on the board and then we can start our argument. So this condition of the wedges being different sizes is equivalent to looking at this picture where the wedges are all the same size, but then just take out any of the symmetry. So that's what we're going to do here. And I'd like to point out that there are 2 main colorings that we need to consider. One coloring where all of the colors are opposite each other. So let's get that drawn right here. So that means if we have blue in this wedge, then we have to have blue in this wedge. If we have red in this wedge right here, then that means we have to have red in this wedge right here. And then if we have green in this wedge, we have to have green in this wedge. And now we'll argue how many of them look like this. So let's start at a blue wedge. We know there has to be a blue wedge. And let's notice that if we count clockwise from blue, there will be 2 choices for the color of this wedge, and then 1 choice left over for the color of this wedge. So that means that counting clockwise from blue, there are 2 choices of coloring. But now we can count the other types of colorings like this via a rotation argument. And so we've got the coloring that's exactly in this position, and then this 1 tick rotation, and then this 2 tick rotation where we rotate the blue into the red or we rotate the blue into the green. So I'll just put here rotations give us 3 more possibilities. So that means down this line there are 6 total colorings if we have each color opposite itself. Now, I'll let you argue that you have to have at least 1 color opposite itself, and that'll be the next case that we look at. If you try to make a coloring where none of the colors are opposite themselves, you'll see that something breaks down. Okay, so now let's look at this setting where only 1 color is opposite itself, and here we're choosing it to be blue. So that means that we have a choice here of red or green. Let's just say that it's red. But then since red is not opposite itself, we know that red has to go here. But that means that these last 2 are green. And now we can make the following argument. We'll choose the color that is opposite itself. So I'll just put here color opposite to talk about that choice. We've got 3 choices of which color is opposite itself. Here we chose blue, but we could choose red or green. And then we'll choose the color clockwise from blue, just as we did before. We have 2 choices of the color clockwise from blue. And then we'll rotate into the positions just as we did over here. And so there'll be 3 total rotations. So now your total possibilities that look like this are kind of pretty clearly equal to 18. So now summing those 2 possibilities, you'll see that there are 24 total colorings. So for the next problem, let's consider a decreasing sequence of n positive integers. So x1 is bigger than x2, is bigger than x3, so on and so forth. And they satisfy the following 2 conditions. The arithmetic mean of the first 3 terms is 2025. And then for k bigger than or equal to 4 but less than or equal to n, the average of the first k terms in this sequence is 1 less than the average of the first k minus 1 terms. And then our goal is to determine the greatest possible value of n. So we've got this sequence x1, which is bigger than x2, which is bigger than x3, so on and so forth. All of those are bigger than xn, and then this is a sequence of positive integers, so we know that xn is bigger than or equal to 1. So let's see, that first condition tells us that x1 plus x2 plus x3 over 3 is equal to 2025. The average of those 3 is 2025. Notice that means that x1 plus x2 plus x3 equals 3 times 2025. That's another way of writing that down. Then let's look at this other condition about the sum of the first k terms. So we know that the average of the first k terms, so that would be x1 plus x2 all the way up to xk over k, is going to be 1 less than the average of the first k minus 1 term. So that's going to be x1 added all the way to xk minus 1 over k minus 1 minus 1. So now what we'll do is, well, put these 2 conditions together to give us this big list of the average of the first 4, the first 5, the first 6, so on and so forth. But we'll take each of those averages and then rewrite them as maybe just the sum of the first 4, 5, 6, so on and so forth. Okay, so let's see. We know from our given that x1 plus x2 plus x3 is 3 times 2025. And then we'll know that x1 plus x2 plus x3 plus x4 is going to be 4 times 2024. That's exactly from this condition right here, just written out a little bit differently. And then we know that x1 added up to x5 is going to be 5 times 2023, because the average of those numbers is 1 less than the average of the one above, which was 2024. Now, if we go down here to the k minus first case, we'll see that the sum of x1 up to xk minus 1 is going to be equal to k minus 1 times 2028 minus k plus 1. You can kind of see that happening already. Notice the sum of the first 3 is 3 times 2028 minus 3. The sum of the first 4 is 4 times 2028 minus 4, so on and so forth. That would be the k minus 1 case. So notice that the k case will be x1 added up to xk will be k times 2028 minus k. But now notice we've got this system of equations that we can use to solve for xk. Maybe we could do it in a couple of special cases up here. Notice that we can take the difference of these two equations and we'll see that we'll get x4 is going to be 4 times 2024 minus 3 times 2025. You can calculate that to be 2021. And then you can take the difference of these two equations to get x5, and you'll see that in this case, x5 will be 2019. But now you can keep doing that, and you'll see that this kth case will give us xk equals 2029 minus 2 times k. That's just the calculation that you get from doing that. But now notice that the largest value of n that is possible will be achieved if x sub n is equal to 1. So let's see, if x sub n is equal to 1, that gives us this nice equation, 2029 minus 2 times n is equal to 1. But we can calculate that pretty easily, and we'll see that n will be equal to 1014. A container has a 1 by 1 square bottom, a 3 by 3 open square top, and 4 congruent trapezoidal sides as shown. Starting when the container is empty, a hose that runs water at a constant rate takes 35 minutes to fill the container up to the midline of the trapezoids. How many more minutes will it take to fill the remainder of the container? Okay, so let's get a picture of this situation on the board. Okay, so here's a picture of our situation, and what I've done is I've extended this down so that we've got an upside down pyramid with a square base. So let's recall that the top of this thing is a square that's 3 by 3. The bottom, before the extension, is a square that's 1 by 1. And so that means that this point in the middle is going to be a square that's 2 by 2, just by some sort of similar triangle argument with maybe the large triangle and the smaller triangle. And then if we put a measurement here that's h, and so that would be like the distance from the top square to the midpoint, which means we've got another distance here, h, which would be from the midpoint to the bottom of the thing. Then, because this is a square with side length 3, this is a square with side length 1, again, by a similar triangle argument, that means that down to the base of the pyramid will be a further distance measurement of h. But now let's calculate the volume of the whole pyramid. And this is just from a standard formula. So what we'll get here is 3 squared, because that's the area of the base here, times 3h over 3. So it's really going to be the height over 3, but our height is 3h. And so this is pretty clearly equal to 9 times h. Okay, but now what about the volume of, let's say, the bottom 2/3. So I'll just put 2 over 3 here for the volume of the bottom 2/3, and maybe let's just indicate that that is the volume of this bit right here. And so we can use our same formula. So that's going to be 2 squared times 2h over 3, because now our base is 2 by 2 square. And so if we calculate this, this is going to be 8h over 3. And then finally, this remaining bit right here, which is what we're cutting off, if you will. So I'm just going to write this as the volume of the bottom third is going to be h over 3 using the same formula. But now we can do a quick calculation and we'll see that the volume of this bit, so I'll just put volume of the middle perhaps because it's the middle portion. So that's going to be 8h over 3 minus h over 3, so that's going to be 7h over 3. Okay, so let's maybe put a box around that because that's going to be an important piece to keep in mind. And then let's talk about the volume of this top bit as well. And we can calculate that as the volume of the whole thing minus the volume of the bottom 2/3. So I'll just put this as V sub t for volume of the top. And that's going to be 19h over 3. So again, that's just from that difference that we talked about before. What is that going to be? Something like 9h minus h8 or 8h over 3. Okay, nice. Okay, so now what we know it took 35 minutes to fill up this portion right here. Now we need to know how much it takes to fill up this portion right here. Keeping in mind it's going to be the same rate of fill. And so what we'll have is 35 times the ratio of this VT with VM. So let's see, we're going to have 35 times 19h over 3 over 7h over 3. So notice the h's cancel, those 3's cancel, this 7 cancels the 35 down to a 5, and we're going to end up with 19 times 5. So 19 times 5 is 95. So it'll take 95 minutes to do the remaining of the fill. An analog clock starts at midnight and runs for 2025 minutes before stopping. What is the tangent of the acute angle between the hour hand and the minute hand when the clock stops? Okay, let's get a picture of this clock on the board. Okay, so there's a picture of our clock. Notice I've put the hours 9, 10, and 11 on the clock for reasons that'll be clear pretty quickly, and that's because this thing is running for 2025 minutes. So we need to figure out what that'll show up on the clock, and we can do that by determining how many hours it is and with the minutes left over. So let's notice that we can write 2025 as 33 times 60 plus 45. So that means that the minute hand will be pointing towards this 9 because we've got 45 minutes left over after we've gone through all of our hours. So let's just put our minute hand here in magenta. Okay, so I'll make it maybe a little longer than it would be just so that it's clear. Okay, so there's our minute hand. And notice we've got 33 hours. So this is the number of hours that we have. But let's notice that 33 hours is going to be what? So 33 hours is going to be 1 day. So 1 times 24 hours plus 9 additional hours. So that means that what we'll see on the clock is evidence of 9 hours passing. But you might say that means that the hour hand points straight to the 9. But the hour hand only points straight to the 9 if you're exactly at 9 o'clock. The hour hand moves a little bit each minute. That's because it's an analog clock. And so how much will it move by the point that we get to 45 minutes? Well, it's going to move 3/4 of the way between 9 and 10. So I'll put 3/4 maybe like this. So the hour hand will be something like this right here. And now we need to calculate what that angle is. Well, let's observe that the angle between 9 and 10 is 30 degrees. That's because we're going around a full 360 degrees for the circle, cut into 12 pieces. 360 divided by 12 is 30. And so what this is right here is 3/4 of 30. So I'll just put 3/4 times 30 degrees. And I'm going to write it like that because we can use an identity to calculate the tangent of 3/4 times 30 without actually writing it out as, what would that be? So like 90 over 4 degrees. Okay, so let's point out that what we need is tangent of 3/4 times 30 degrees, but that's going to be the same thing as the tangent of 1/2 of 45 degrees. just by some simple arithmetic. And now we can use a half angle identity for tangent. So that's going to end up giving us 1 minus the cosine of 45 degrees all over the sine of 45 degrees. But the cosine of 45 degrees and the sine of 45 degrees are well known to be the square root of 2 over 2 or 1 over the square root of 2. I'll use 1 over the square root of 2. So that means we have this object right here, 1 minus 1 over the square root of 2 over 1 over the square root of 2. But after some simplification, we'll get that this is the square root of 2 minus 1. Each of the 9 squares of a 3 by 3 grid is to be colored red, blue, or yellow in a way that each red square shares an edge with at least one blue square. Each blue square shares an edge with at least one yellow square, and each yellow square shares an edge with at least one red square. Colorings that can be obtained from one another by rotations and or reflections are considered to be the same. How many different colorings are possible? So let's observe that we've got this cycle occurring. So red squares have to be connected in a way to blue squares, and blue squares have to be connected in a way to yellow squares, and then yellow squares have to be connected in a way to red squares. So this is kind of like some sort of digraph relationship right here. Notice that the arrows go in one direction. So red squares need not share an edge with a yellow square. A yellow square just has to share an edge with a red square. But we've got some symmetry into this situation. And perhaps the symmetry is a little bit more obvious if we erase that red at the end and observe that what we have here is this kind of loop. So red goes to blue, blue goes to yellow, and yellow goes back to red. So we can really start at any point in this loop and we've got the same sort of relationship. And so that gives us our first choice, and that choice will be the choice of the middle color. So I'll just put here where you need to choose the middle color. And there's kind of obviously 3 choices for the middle color: red, blue, or yellow. But those are all like kind of symmetric in a way to each other, in that choosing red, blue, or yellow will give us the same number of outcomes in the end. And again, we only really need to talk about choosing the middle color and see what's arising from choosing the middle color, because rotations and reflections are considered the same coloring, if you will. Okay, so let's get this partitioned out right here. So there we've got this. So let's say we choose the middle color to be red. Just kind of without loss of generality, that's the choice that we have made. Like I said, we'll get similar pictures if we choose blue or yellow. And so notice that red has to share an edge with blue. So that means this square right here to the right, to the top, to the left, or to the bottom has to be blue. But again, since we're symmetric up to rotations and reflections, we might as well choose this square right here to be blue. But then blue has to share an edge with yellow. That means this one above or below has to be yellow. But again, because we're symmetric about rotations or reflections, we might as well choose this one up here to be yellow. And then yellow has to share an edge with red. So that means this one right here has to be red. And then red has to share an edge with blue. So that means this one right here has to be blue. And then blue has to share one with yellow. So that means this one right here has to be yellow. So after choosing the middle color to be red or blue or yellow, we end up with the top portion of the square completely filled in. And now what we'll do is build off what choice we make for this bottom left square. So here, I'm just gonna take this into 3 directions, and I'm gonna copy my square over and then look at what happens if I choose this to be red, blue, or yellow. Okay, so I copied up my square over into 3 new squares, and that's gonna be based on the choice that I make for this bottom left subsquare. So let's say that we choose this to be yellow. Okay, so if we choose this to be yellow, then that means this next one has to be red. But now let's look at this. If that next one is red, then red has to be connected to a blue. So that means this one right here has to be blue. But then blue has to be connected to a yellow. But if I color this blue, which it has to be because of the red right here, the blue will not be connected to a yellow. So that means we've reached an impossibility here. So I'll just put like an X here in that there's nothing to color that subsquare that will make the rules satisfied. Okay, so now let's go down to this one right here, and let's say we fill in a red for our bottom square, but then red has to be attached to a blue, so that means this one right here has to be a blue, but then blue has to be next to a yellow. So that means this square here has to be yellow, but then yellow has to be next to red. But if I color this yellow, it is not next to a red. So I'll just put an X right here as well because there's nothing to color this square which will satisfy the rules. Okay, so that means that right here I must put a blue. But now what do we have? We've got blue is next to a yellow already, but since it's next to a yellow already, I've got choices right here. I could make this red, blue, or yellow. So let's bring that out into our three choices and see which ones are possible. Okay, so now for our next choice, which will be this middle square in the bottom row. Okay, so let's say we were to choose this to be blue. Well, then blue squares have to be next to yellow squares. That means this one right here would have to be yellow. But then yellow squares have to be next to red squares, but this is not next to a red square. That means we have an impossibility here. Okay, so now let's move back down to this next one. And let's say that we choose this next to be red. Okay, then notice that red squares have to be next to blue squares. This is already next to a blue square. So that means that I can put anything here that I want. Well, almost anything here that I want. I can't put a blue square because it would not be next to a yellow square. But in fact, it's possible to put a yellow square here and a red square here. That satisfies the conditions that we need it to satisfy. And so that means that down this path, there are two choices. The two choices are this red square or this being a yellow square. Okay, now let's move down to this last case. Let's say we were to fill this in with a yellow. So notice filling this in with a yellow, it's impossible to fill this lower square in with a yellow because it would not be next to a red. But it is possible to fill it in with either a red or a blue. Both of those satisfy the conditions that are outlined here. So both of those are possibilities, like I said. So that gives us two more choices. So let's count up our choices. We've got three choices for the middle color. And then at the end of these branches, we've got two choices here and two choices here. So in the end, there are 3 times 2 times 2, or in other words, 12 total colorings. Onic repeatedly plays a game with a probability of winning 1/3. The outcomes of the games are independent. What is the expected value of the number of games he will play until he has both won and lost at least once? Okay, so let's lay this out. So he must play at least 2 games. So I'll just put here the probability of playing 2 games. So let's read that as the probability of playing 2 games and stopping. And so that means that this is going to be equal to the probability of winning the first game and losing the second game, plus the probability of losing the first game and winning the second game. So those are the 2 ways to play only 2 games. But let's observe that this is simply going to be 1/3 times 2/3 plus 1/3 times 2/3. In other words, it's going to be 4/9. Because if the probability of winning is 1/3, then the probability of losing is 2/3. Okay, so now what about the probability of playing 3 games before that condition is satisfied, winning 1 and losing 1? And so how could you do that? Well, you could win games 1 and 2, and you could lose game 3. That would be one way to do it. Or you could lose games 1 and 2, and you could win game 3. So let's see, this is going to be 1/3 times 1/3 times 2/3. In other words, it's going to be 2 over 27 plus, so this is going to be 2/3 times 2/3 times 1/3. So that's going to be 4 over 27. And so you might put that together into 6 over 27, but let's leave it like that. Okay, so now let's move down here to the probability of having to play n+1 games. And so how could you do that? Well, you could win games 1 through n, and then you could lose game n+1, or you could lose games 1 through n, and you could win game n+1. Those are the two ways that this could occur. And so let's observe that there are going to be 2 over 3 to the n+1. That's the probability of this first condition, because let's see, you're gonna only lose this last one. That gives you a 2 over 3 to the n, or sorry, a 2 over 3. And then here you've got a 1 over 3 times 1 over 3 times 1 over 3 n times. And then to that, we have to add 2 to the n over 3 to the n+1 for similar considerations. Okay, so now we can figure out the expected number of games. So I'll just put here expected number of games. So that's going to be equal to the sum as n goes from 1 to infinity of n+1. So that's the number of games played times the probability of playing those number of games. So n+1 games times 2 over 3 to the n+1 plus 2 to the n over 3 to the n+1. So something like, now this is maybe like close to a formula that you might know, but you can also do a little calculus to calculate this. So what I would do is I would rewrite this as 2/3, and then the sum as n goes from 1 to infinity of n+1 times x to the n evaluated at x equals 1/3. And so that would be like from this first part of the sum. And for this next bit, I would write that as 1/3, and then the sum as n goes from 1 to infinity of n+1 times x to the n evaluated at x equals 2/3 for the second bit of that sum. Okay, then, well, what would I do from there? Well, I'd like to observe that this is equal to 2/3 and then times the derivative with respect to x of the sum as n goes from 1 to infinity of x to the n+1 evaluated at x equals 1/3. That's how I want to read this n+1 out front, as if a derivative has occurred. And then here we're going to have plus 1/3, and then the derivative with respect to x of the sum as n goes from 1 to infinity of another x to the n+1, and then evaluate it at x equals 2/3. But now what this turns into is 2/3, and then the derivative with respect to x of x squared over 1 minus x evaluated at x equals 1/3, and then plus 1/3, and then the derivative with respect to x of another x squared over 1 minus x. And then this is going to be evaluated at x equals 2/3. Now, perhaps I'll leave it to you to do the rest of the calculation right here, but what you end up in the end with is 7/2. A rectangular grid of squares has 141 rows and 91 columns. Each square has room for 2 numbers. Horace and Vera each fill out the grid by putting numbers 1 through 12,831, which is 141 times 91, into the squares. Horace fills the grid vertically. He puts 1 through 91 in order from left to right in row 1, 92 to 182 in row 2, and so on and so forth. Vera fills the grid vertically. She puts 1 through 141 from top to bottom in column 1, 142 to 282 into column 2, and so on and so forth. How many squares get 2 copies of the same number? Okay, let's get a picture of this on the board. Okay, so there's our picture of our grid. So I'm gonna fill in numbers in yellow for Horace and blue for Vera. So let's just kind of get a picture of what's going on here first, and then we can move on to the next step. Okay, so there's like a quick just fill in of what this might start to look like. But from this, we can pretty quickly write down what's going on in the MN location. So let's observe that in the MN location, Horace writes the number 91 times m minus 1 plus n. So m is controlling what row you're in, and n is controlling what column you're in. So notice in the first row, we just get n right here for whichever column you're in. And in the second row, we'll get 91 plus whichever column you're in, and so on and so forth. And then, well, what about for Vera? Well, it's gonna kind of be the dual of this, keeping in mind that we have 141 rows. So this is gonna be 141 times n minus 1 plus m. Like I said, it's like the dual or the transpose of this or something. And now let's observe that in both of these cases, m is running from 1 to 141, and n is running from 1 to 91. Okay, so let's maybe give this a name right here. Let's say that this is Horace at mn, and let's say that this is Vera at mn. Good. And now what we want is for these two to be equal to each other. So I'll just put this down here. What we want is 91m minus 91 plus n. That's what I get from just multiplying out that thing for Horace, is equal to 141n minus 141 plus m. Okay, nice. But now we can do some pretty simple arithmetic to this, and you'll see that you get 14n minus 9m is equal to 5. So again, that's just from moving some things around. But now let's observe that if we go modulo 9, this is going to turn into 14n is congruent to 5 modulo 9. But then 14 is just the same thing as 5 mod 9. So that means that this is 5n is congruent to 5 mod 9. But then we can divide both sides by 5, if you will. And what we'll get is that n is congruent to 1 mod 9. So that means that n must be of the form 9k plus 1. And then if we likewise go mod 14 here, that's going to simplify into minus 9m, but negative 9 mod 14 is in fact just equal to 5. So we'll get 5m is congruent to 5 mod 14. But that means that m is congruent to 1 mod 14. But that means that m is equal to 14l plus 1. And so that means that these are going to overlap when n is 9k plus 1, of the form 9k plus 1, and when m is of the form 14l plus 1. But then, since these have to satisfy this single equation up here, that means that this L is not really totally free to be chosen. It has to be chosen to be the same K that we had over there for our choice of N. In other words, this equation right here now looks like 14 times 9k plus 1 minus 9 times 14k plus 1 equals 5. But that equation is satisfied for all k between 0 and 10. Well, it's actually satisfied for all integers k, but those values of k between 0 and 10 will correspond to squares in our diagram up here. And so the answer here is 11, because notice that we've got 11 choices for k. A frog hops along a number line according to the following rules. It starts at 0. If it's at 0, then it moves to 1 with a probability of a half and disappears with a probability of a half. For n equals 1, 2, or 3, if it's at n, then it moves to n plus 1 with a probability of a quarter, and it moves to n minus 1 with a probability of a quarter, and it disappears with a probability of a half. What's the probability that the frog reaches number 4? Okay, so here's what we're going to do. Let's define this function p of n, and this function p of n will be the probability that the frog moves from point n on the number line to point 4 on the number line. So let's observe that what we want is p of 0, because we know that our frog starts at 0, and we want the probability that the frog is going to move to the number 4. Okay, so what do we know? Well, we know what happens if the probability, if the frog is already at 4. Well, the probability it gets to 4 is 1. So in other words, p of 4 is equal to 1. Now let's look at the probability that the frog moves from 3 to 4. Well, that's going to be equal to the probability that it goes from 3 straight to 4 plus the probability that it goes from 3 back to 2 and then somehow from there gets to 4. Well, let's observe that the probability that it goes straight from 3 to 4 is a quarter. That's within our rules. And then the probability that it goes from 3 back to 2 is also a quarter. And then the probability that it then goes from 2 to 4 by any means necessary is going to be p of 2, because that's, well, the function that we're building. So now you can kind of see what we're doing here. We're building this nice kind of recursive relationship between all of these p of n's. Okay, so now let's look at p of 2 using a similar argument. So let's say the probability that it goes from 2 to 3 and then somehow goes to 4 plus the probability that it goes from 2 back to 1 and then somehow goes to 4. So those are the two possibilities here for it to get to 4, of course. But notice that that's going to be equal to a quarter times the probability of 3, because it has a quarter chance of going to 3. And then, well, once it's at 3, it has to get to 4 somehow. It's got a probability of p of 3 of getting there. And then plus a quarter the p of 1 for the same kind of argument right here. Okay, so now let's look at p of 1 similarly. So notice that p of 1 is going to be 1/4 times p of 0. That's like if it went back to 0 and then somehow got to 4, plus 1/4 p of 2. That would be like it took a hop to 2 and then somehow got to 4. And then what about the p of 0? That's going to be 1/2 times p of 1. Because the frog can't move backwards from 0. In order to get to point 4, the only step that it can make is towards point 1, and the probability of that occurring is 1/2. Okay, so now that we've got all of these relationships between p0, 1, 2, 3, and 4, let's maybe summarize those at the top and then solve the system of equations. Okay, so there's a summary of what we just had. So now what I'm going to do is start at the top and then just eliminate some of these variables or values of the function as needed. Here we see that p of 2 will be 7 times p of 0. And so that's just perhaps solving p of 2 in terms of p of 1 and p of 0, and then making the substitution right here where p of 1 is 2p of 0. Okay. And then, well, we can do something similar here for our p of 2 and p of 3 now. Well, we can plug in what we have for p of 2 and what we have for p of 1 into this equation right here and solve for p of 3. So I'll let you do that. That's just some straightforward kind of arithmetic. And what you'll get is p of 3 is 26p of 0. But now we've got these two equations for p of 3 that we can use to solve for p of 0. Keeping in mind that perhaps we would put this value of p of 2 into this equation for p of 3. So in the end, we'll see this. We'll see that 4p of 3 minus p of 2 is equal to 1. So that's just from rearranging this equation. And then what we'll do is replace this p of 3 with what we have above. So that's going to be 4 times 26 p of 0 minus 7 times p of 0 is equal to 1. Again, that's just from the equations that we've already developed. But now, doing some straightforward arithmetic, what we'll find is p of 0 is 1 over 97. Two non-congruent triangles have the same area. Each triangle has sides of length 8 and 9, and a third side of the triangle has integer length. What is the sum of the lengths of the third sides? Okay, so not strictly necessary. Let's draw two triangles on the board just so that we can visualize what's going on. Okay, so there we have our triangles on the board just for visualization. And now what we'll do is take the area of these triangles, well, not exactly the area of these triangles, the square of the area times 2, and that's because that simplifies all of the parts involved inside of Heron's formula. And so we're going to use Heron's formula to calculate the area of each triangle. We'll square that and multiply by 2, and that'll pretty quickly bring us to the following equation. So we'll have x plus 17 times x plus 1 times x minus 1 times 17 minus x equals y plus 17 times y minus 1 times y plus 1 times 17 minus y. And so that would be the area of this left-hand one, and that would be the area of this right-hand one. And just recall that we were given that those two areas were the same. And so now I'd like to pretty quickly observe that that tells us that x and y are between 2 and 16. So what we want to do is find values of x and y that are different that make this type of product equal. So I think probably your best bet here to do this quickly is just via guess and check. And if you look at perhaps like x equal 11, you'll get this simplifies to the following object. So we'll have 6 times 10 times 12 times 28. And then if you have perhaps y equals 13, that's going to simplify to 4 times 12 times 14 times 30. And then you can check just via some straightforward arithmetic that these are equal. So that tells us that our side lengths are 11 and 13. But of course, we're looking for the sum 11 plus 13, which is 24, because that's what the problem was asking for. So there's actually another strategy here, which we can get if we assign perhaps alpha to this angle and beta to this angle, and then use the fact that the area of these triangles can be expressed as 8 times 9 times the sine of alpha. And that's not exactly the area, that's a scale of the area again. And so that's going to give us a different type of solution here. So I'll just put here or. We know that 8 times 9 times the sine of alpha. In other words, 72 times the sine of alpha equals 72 times the sine of beta. In other words, we know that the sine of alpha equals the sine of beta. And since alpha and beta are between 0 and 180 degrees, that in fact tells us that alpha and beta are supplementary. So they add to 180. And from that, we can take these two triangles, duplicate them, and glue them together into a parallelogram. So it would, in the end, look a little bit like this. So we would have perhaps this would be angle beta, this would be angle alpha, so that's angle alpha, that's angle beta. And then let's see, we've got something like this. So we've got that this out here is length y, this is length x, this is length y, and this is length x. And then the diagonals have length 18 and length 16. That's because it's just the double of these sides right here. And then you can use this formula that relates the diagonals of a parallelogram and the sides of a parallelogram to get the following equation. So we have 2 times x squared plus y squared equals 16 squared plus 18 squared, because those are those two diagonals like I spoke about before. But pretty quickly that shows us that x squared plus y squared is in fact equal to 290. And then from there you can go about just guessing and checking your sums of perfect squares between 2 and 16 to get a sum of 290, and you'll see that x is perhaps equal to 13 and then y is equal to 11. That works. But then again, we're looking for the sum of those two, which is 24. What is the greatest possible area of the triangle in the complex plane with vertices 2z, 1 plus I times z, and 1 minus I times z, where z is a complex number satisfying the condition, the modulus of 4z minus 2 is equal to 1. So I'd like to notice that the triangle with vertices 2 times z, 1 plus I times z, and 1 minus I times z is just a scaled and rotated copy of the triangle with vertices 2, 1 plus I, and 1 minus I. And it's scaled by the modulus of z, and it's rotated by the argument of z. So that's just like a well-known result that multiplying by a complex number z scales by the modulus of z. In other words, it increases the distance from the origin by a factor of the modulus of z, and then it does this rotation by the argument, or the polar angle, if you will, of that complex number. So that means if we look at this triangle and find its area, the area of our triangle will simply be scaled by the modulus of z squared. Okay, so let's look at the area of this triangle right here. So we'll go out here to the number 2, so that's one of our vertices. And then 1 plus I is a vertex, and then 1 minus I is a vertex. Okay, so the triangle looks something like this. The area is 1. And you can see that that's just 1/2 base times height. So you can take the base as this side right here, that is 2 units. And the height is pretty clearly equal to 1 unit. So 1/2, 2 times 1 is 1. So that means our final area is the modulus of z squared. Now we've got to think about that second condition. So we were given that z satisfies the equation 4z minus 2 equals 1. So what I'll do is I'll divide both sides of this by 4, and that'll give us the modulus of z minus 1/2 equals 1/4. But it's pretty well known that that's the equation of a circle in the complex plane, where the center is at the point 1/2 and the radius is 1/4. So if we sketch that out, so let's go here and put 1/2, then here we'll put 3/4, and then over here we'll put 1/4, and observe that we've got a circle like this. Okay, so that's not a great picture, but that gets the idea. Now what we want to do is pick a point along this circle that is furthest away from the origin. In other words, it has the biggest modulus. But if you kind of sketch out a circle of radius 3/4, you'll see that the point with the largest modulus is this point right here, z equals 3/4. But let's recall that we were trying to maximize the final area of this triangle up here, and that maximization will occur when the modulus of z is largest, and we just described that that will occur when z equals 3/4. And that will give us a final area of, well, notice it's just 3/4 squared. In other words, it's 9/16. Let S be the set of all integers z bigger than 1, such that for all pairs of non-negative integers x and y, with x less than y less than z, the remainder of 2025x when divided by z is less than the remainder of 2025y when divided by z. What is the sum of the elements of S? Okay, let's get a condition for what it takes to be inside of S. So let's observe that if we have z inside of S, that tells us for all x less than y less than z, there exists Q1 and Q2 and R1 and R2. Those are all integers and they satisfy this rule. So 2025x equals Q1z plus R1 and 2025y equals Q2z plus R2. And that's going to be with the following condition. And that is that 0 is less than or equal to R1, which is less than R2, which is less than z. And so the remainder R1 being less than the remainder R2 is given, and then just facts about remainders, like the sizes of remainders given what you are dividing by, is what's giving us both of these are between 0 and z. But now what I'm going to do is apply this condition to all n and n plus 1 with, let's see, 1 less than n less than z. And well, that's because this has to hold for all x and y less than z. So we might as well take x to be n and y to be n plus 1. Okay, so that's going to give us the following setup. So for instance, with x equal to 1 and y equal to 2, we get the equation 2025 equals q1 times z plus r1, and 2 times 2025 equals q2 times z plus r2. And this is, of course, with our inequality right here. So 0 is less than or equal to r1, which is less than r2, which is less than z. But now we just trade the roles. So this was set up where x was equal to 1 and y was equal to 2. Now let's do the setup where x is equal to 2 and y is equal to 3. So that's going to give us 3 times 2025 equals q3z plus r3. And then from these two, we get 0 is less than or equal to r2, which is less than r3, which is less than z. But now we'll just continue. We'll switch the roles of x and y. So now x will be 3 and y will be 4, and then so on and so forth. So let's do that one next. So we'll have 4 times 2025 equals q4z plus r4. And here we're going to see that 0 is less than or equal to r3, which is less than r4, which is less than z. And this is going to go all the way down until the largest value of y. And the largest value of y will be z minus 1. And so at the end, we'll have z minus 1 times 2025 equals q sub z minus 1 times z plus r sub z minus 1. And now we'll have a string of inequalities that are built from all of these. So I'll just put them all together. Notice that we could put these first three together kind of clearly. We'll have R1 is less than R2, is less than R3, is less than R4. So in the end, we've got this set of inequalities. 0 is less than or equal to R1, which is less than R2, which is less than R3, which is less than R4, all the way up RZ minus 1, which is strictly less than Z. But now let's observe that if R1 is equal to 0, then we get Z as a multiple of 2025, which means it's a multiple of 2 times 2025, which means R2 is 0. And in turn, R3, R4, all of the R's are 0. And so that stuff that I just said explains why R1 is not equal to 0. But then if R1 is not equal to 0, what we can do is exchange this for a strict inequality. So let's observe that we've got Z minus 1 numbers between 0 and Z. But that tells us that R1 must be equal to 1, and R2 must be equal to 2, R3 must be equal to 3, and so on and so forth. So R sub Z minus 1 has to be equal to Z minus 1. So now let's take a summary of that fact that we've just discovered and finish it off. So we've shown that our condition on elements of S leads to the following fact. So if Z is an S, there exist these quotients Q1, Q2 up to Q sub Z minus 1 such that 2025 is equal to Q1 times Z plus 1. 2 times 2025 is equal to Q2 times Z plus 2. And so on and so forth up to Z minus 1 times 2025 equals q sub z minus 1 times z plus z minus 1. But now what I'd like to do is maybe invert each of these. So what I mean by that is I'm going to move the remainders to the left-hand side of the equation. But let's observe that that means that q1 times z is equal to 2 times 2024. That tells us that q2 times z is equal to 2 times 2024. Because let's observe that we're taking 2 times 2021 minus 2 times 1. And so on and so forth down here to q sub z minus 1 times z is equal to z minus 1 times 2024. So let's observe that an important takeaway from this is that z must divide 2024. Recall that z was not allowed to be 1, so the smallest divisor we can look at is 2. So that means that z is from the set 2, 4, 8, 11, 22, 44, 88, and then 23, 46, 92, 184, and then 253, 506, 1012, and 2024. So that's the set of all the divisors of 2024 except for 1. And so now if we take the sum of these, which is what the question is asking for, you'll see that this is 4,319. Another strategy that we could do is use the sum of divisors function. So we'll have sigma of 2024, and then we've got to subtract 1 because we have to subtract the fact that we're not allowed to use the divisor 1. But let's observe that 2024 has the following prime factorization. So it is 2 cubed times 11 times 23. But then this sum of divisors function is in fact a multiplicative function. So this is sigma of 8, sigma of 11, and then sigma of 23. And then of course we have to subtract 1. But then it's pretty easy to find sums of divisors of these. In fact, there's like a nice formula, which I'll let you look up if you want to. The sigma of 8 is 1 plus 2 plus 4 plus 8. Those are the divisors of 8. And then for 11, we have 1 plus 11 because it's prime, 1 plus 23 because 23 is prime, and then minus 1. But then if you make that calculation, you of course get this same number that we had above. How many real numbers satisfy the equation sine of 20 times pi times x is equal to the log base 20 of x? So let's get a quick intuitive sketch of this graph, and then I think that makes the counting a lot easier. So here's a by no means to scale kind of intuitive picture of what's going on here. So here we have that log base 20 function. So notice it goes through the point 1 over 20 comma negative 1. It goes through the point 1, 0, and 21, just by rules of logarithms. And then here's my sine function. So notice it does its first full period between 0 and 2 over 20. So that means it goes through the x-axis at 1 over 20, and then notice that it will cross the graph twice between 1 over 20 and 2 over 20. And then it'll skip crossing the graph between 2 over 20 and 3 over 20 because it's above the x-axis, but the logarithm function is below the x-axis. It'll actually hit the graph 2 more times between 3 over 20 and 4 over 20, and so on and so forth. So between an odd number over 20 and an even number over 20. So that of course occurs until we hit 1, where it starts crossing the graph like above the x-axis. So let's just observe that it's going to cross 2 times on the following intervals. And those intervals are going to be 1 over 20 to 2 over 20. And so that would be from this point to this point, and then again from 3 over 20 to 4 over 20. So that's kind of not drawn in the graph, but that would be similar to this picture right here. And then 5 over 20 to 6 over 20. And then the last time it does this is between 17 over 20 and 18 over 20. That's because something different happens right here at 20 over 20 because it goes through the x-axis. And so how many crossings is this? Well, let's observe that this is going to be 2 times 9, or 18 total crossings. That's because there are 9 subintervals there, and it's crossing 2 times. And then let's observe that it crosses 1 time on the interval 19/20 to 20/20, and that's an open interval. And that would be maybe the upshot of this portion of the curve right here. So it's not on the graph, but maybe we could extend it up just for visualization purposes. That would be that crossing. But it only crosses once because then it crosses again at 1. In other words, 20/20. And so I'll just say 1 time at x equals 20/20, or in other words, 1. And then an additional 1 time right here. So that's going to be between 20/20 and 21/20. That's going to be from this down slope right here. So I'll just say on the interval 1 to 21/20. So all together from these kind of strange middle crossings, if you will, this thing that's happening at this, well, it's nowhere near kind of the midpoint, but it's what's happening kind of in the change of behavior. There are 3 crossings. And then it's going to have a pretty similar crossing behavior above the x-axis that it had below the x-axis that we talked about first. So I'll just put here 2 times each on the following intervals. So 22/20 to 23/20, and then 24/20 to 25/20, all the way up to the last interval that it crosses on will be 398/20 to 399/20. So that's not the last possible subinterval that we might think of, but notice that it is below the x-axis on this last bit, so it doesn't give us any crossings there. And so now let's observe that how many subintervals are there in this piece? Well, there are going to be 189 subintervals, and we get 2 crossings for each subinterval. So that's going to give us 378 total intersection points. And so now in total, adding these 3 flavors of intersections together, we have 18 plus 3 plus 378. But of course, that's going to be equal to 399 total crossings of these 2 graphs. 3 concentric circles have radii 1, 2, and 3. An equilateral triangle with side length s has 1 vertex on each circle. What is s squared? So this is one of those problems that appears from time to time, and so it's kind of useful to know how to do this. So here's my picture of this situation. So I've got my circle of radius 1, 2, and 3, and here we've got our equilateral triangle. And so the trick here is to complete this into a quadrilateral. So let's go here to the center, which I'll call O, and then connect C with O, and then B with O. Good. And then we'll use something called Ptolemy's theorem, and it says that the quadrilateral ABOC is cyclic. In other words, it can be drawn where all the vertices are on a circle if and only if we have the following condition, and that is AO times BC, so the length of AO times the length of CB is equal to the length of BO times the length of AC plus the length of OC times the length of AB. But let's observe that we were supposed to assume that the side lengths of these triangles were S. So that actually gives us this nice equation that is 3 times S. So how do we know that it's 3 times S? Well, notice that the distance from A to O is 3, given the fact that this is the center of the circle of radius 3. And then BC is one of the sides of our equilateral triangle. So anyway, we have 3 times S is equal to 2 times S plus S. That's what those end up being for similar reasons. But of course, that is true. 3 times S is equal to 2 times S plus S. So that means that this is a cyclic quadrilateral. But now we know that inside of a cyclic quadrilateral, opposite angles are supplementary. Again, that's just a geometry fact. But that tells us that the angle BOC, so let's look at that, BOC is opposite angle CAB, but angle CAB is 60 degrees, given that we're inside of an equilateral triangle, so that means that this is angle measure 120 degrees. Okay, so let's fill that in. We know that this is measure 120 degrees. We know that this OC is length 1. We know that this OB is length 2. And we know that this BC is length S. Now we'll apply the law of cosines to this triangle that we've just added all the measurements to. So that's going to give us this equation s squared equals 1 squared plus 2 squared minus 2 times 1 times 2 times the cosine of 120 degrees. So again, that's just putting it into the law of cosines formula. But after some calculation, you'll see that that is equal to 5 minus 4 times negative 1/2. But putting all that together, we get 7. So our final answer, s squared, is 7.